Hi everybody, welcome to new students joining our department here and to those who are returning. It's the first day of school. I've had at least 57 first days of school, something like that. Anyway. But those of you who don't know me, I'm Ivan Deutsch, and I'm the instructor this semester for quantum optics. Andrew Forbes is one of our TAs, together with Vikas Vishnuvari, who will be working together as well in assisting us in this course. So let's see, first orders of business. So all the information, this is probably one of the last times I'll put on the projector here, but I just wanted to begin here because has everyone gone to the course website yet? If you haven't, you should. You can find the link to it on the Physics and Astronomy webpage. In addition, I will email it to you based on that. So it's very important that you have access to the web page because all the materials for the course will be distributed through the course website. And that includes the lecture notes, the assignments, any handouts that they'll be downloadable. In addition, we will be video recording the lectures. They will be behind a firewall, so they're not public. They're for people who have UNM IDs. But at the end of the course, if you are willing and give your consent, traditionally I have posted they used to just be open. Back in, 2002, I started putting my lectures on the web, and I'd get emails from kids all over the world. Some kid in Pakistan says, when are you going to put problem set 7 solution on? And so I love that fact, but sort of up to you whether you feel okay about having your privacy in any way infringed upon. It's fine. We won't do that. Okay, but for your purposes, you will be able to review the lectures as you like once they are posted on the site. And that will be over here. There will be a link once it's live, and you'll be able to click on it, and you will be able to then see the lectures. There'll be links as well. So here you can, for example, download. These are the notes for today's lecture, plus or minus my musings, of which there are many, and you will be able to see the assignments once they're posted down here. Okay? So let's see some other orders of business. So the prerequisites for this course are somewhat flexible. The prerequisite is a year of graduate level quantum mechanics, somewhat equivalent to what's taught in physics 521 and 522 here in the Department of Physics and Astronomy. But it's really up to you. This is not a strict prereq. This is an advanced graduate course, and it's up to you to make your choices. I'll do my best, but there is going to be an assumption that everyone is fairly proficient in quantum mechanics. Okay, that's going to be the requirement. I know that there's a variety of folks at different stages in their education here. Some of you are first-year students, some of you are second, some of you are third year, some of you have lots of background in quantum information science, some of you don't have any. And so there will be something for everyone, I hope. For some folks, some things may be quite a bit of review. For other people, it's going to be very new, but we'll, all kind of converge at some point to equal level. What else? So there are no required textbooks for this course. There will be distributed lecture notes that have all the materials that I will cover in lecture, but it's important to listen to another voice except mine, mellifluous as it might be. And so you really should think about additional sources, and that's sort of up to you. I have some suggestions. Let's see, where are they? Here they are. So here are some of the recommended texts. And I'll explain, they cover different aspects of the broad subject matter of quantum optics as we will cover it in this course. The book by Cohen-Tanucci et al. Really, it's not just Cohen-Tanucci, who the other authors are, they get short shrift. Atom-photon interactions is a standard. Quantum optics by Scully and Zubara is a standard. Marlon Scully actually is interesting. He's one of the godfathers of quantum optics. He was a professor here at UNM back in the 1980s, mostly. And he's kind of the reason there is a quantum information science program here at UNM. It's kind of interesting. So anyway, so yeah, these are some books you could just think about either getting some from the library, or maybe some of them are available in electronic form, or maybe you really like a hard copy, and I recommend some of those. So you can take a look, and I absolutely suggest thinking about looking at some other sources as well. What else? Let's see. So as far as the grading goes, the course will primarily be based on homework. Much of this homework is recycled from previous years because they're pretty good problems, some of them, once I've corrected every typo, but that's never true. It's up to you to do what you think. If you're just copying solutions, we know, don't bother. But it's, again, the grades are not, this is an advanced graduate course. I'm here at this point to share my knowledge as best I can, and your job is to take as much knowledge as you can and do with it what you like. I'm not here. Yeah, we got to give grades. We'll give grades. You got to, you need incentive, but it's on you at this point. Okay. There will be a final project. It might not be. I'm kind of rearranging things a little bit. It may not be the final time of the course. It might be sort of in the middle, latter part of the semester, and we'll talk more about that as the time comes. It will be the basic idea is that you will be writing a Wikipedia page on some topic in quantum optics, and there's a method to my madness for that. So let's talk about that a little while. So homework, there will be homework generally assigned every week, available on the website. It'll be distributed on Thursdays and due the following Thursday. Okay. You can either email it if it's an electronic version, or if it's written, put it in Andrew's mailbox. Okay. It'll be due at 5 p.m. on Thursday. What was I going to say about that? I forgot. Anyway, in addition, we'll have 2 office hours per week. I'll hold 1 office hour, and Andrew and Vikas will share in some way the TA duties for that, and I'll send around a some kind of poll to try to find a time that works at least the best we can, given the 20 folks who are registered for this course. I think a lot of the OSC students are currently in their orientation right now, at least some of the first years. So there might be more people sitting in the room next time. Right. Does anybody have any questions about any of that? The logistics of the course, anything else? Fairly straightforward. Yes, sir.
When we talk about the mailbox, we're talking specifically the physical mailbox?
Yeah.
Or is this also including email?
Yeah, either or. Either or. Either if you have it as a, if you just, you don't need to scan it in, and if you write some people do their homework in LaTeX these days, so you don't need to print it out and put it in Andrew's mailbox, you could just email it to him. There's a link here to his email address, but if you write your homework out with pen or a pencil on a piece of paper, you scan it in, you can put it in the mailbox. All right, good. Let's see, so what else? So let's maybe just get started a little bit talking about the subject matter of quantum optics. So quantum optics, what people call quantum optics kind of varies from person to person, instructor to instructor. I have a pretty broad view of it, and this is a thing I put together umpteen years ago, and I can't even find the original file version, so I can't update it. It's a little bit out of date, but one day I'll be brave enough to recreate it. But what is the point here? Well, what is quantum optics about? Maybe if you just say that. The way we're defining it is the study of quantum coherence in and by electromagnetic fields, or I'll put in quotes here, light. What do I mean by this? Well, sort of the core subject of what people would traditionally call quantum optics is the study of the quantum properties of light. Okay, the fact that light itself is a quantum field, and the nature of that quantum field, is particularly when it comes to light, that is to say, things in the visible range, was the core subject of quantum optics. Of course, quantum electrodynamics was developed in trying to understand the quantum nature of the electromagnetic field and its interactions with charges, but after its development, it was developed in the context, when you think about quantum field theory, you typically think about high energy physics, right? I mean, you think about gamma rays, electrons, positrons. The quantum field theory was developed in order to understand the nature of fields and matter at high energy. And for about 40 years, it was kind of ignored after the development of QED. In what way should we even worry about the fact that light is composed of photons? Because those were thought to be pretty much negligible effects from any measurable or important fundamental quantity. I mean, these days, the reason I put light in quotation marks is that quantum optics isn't interesting and applicable only in thinking about the visible spectrum, but other parts of the spectrum. Even at the microwave level, when we think about, gigahertz, and you think about how, that's a fraction of an electron volt. Why no one would ever have thought I should worry about the quantum nature of microwaves, but in today's superconducting quantum computers, it's really important. And we manipulate lots of things with the quantum nature of the field. So the quantum nature of the field is one aspect, and that's related to the whole story of quantum coherence, okay? So the word coherence is really the unifying concept that we're going to talk about in lots of different contexts. The notion of coherence is a notion that grows out of classical wave theory, but has an important generalization in its context in quantum theory, and particularly in quantum optics. So when I say in, I mean this column here. That is to say, the coherence within the field itself, and the nature of that coherence, and both in terms of understanding its fundamental properties as our understanding of nature, and its potential applications for, in particular, of great interest, and these days is for new information processing paradigms that make use of that coherence in the field. Now, when I say by in this sentence, what I mean is that the fields can be used to create quantum coherence in matter, okay? So the way in which quantum coherence is created in matter by fields is really related in this column, which is to say, when we typically, when traditional spectroscopy, that's to say, the way in which electromagnetic fields were used to diagnose the properties of matter, really had nothing to do with quantum interference or quantum coherence. But the ability to manipulate quantum superpositions in matter by fields became an important tool, and that tool really was the growth in which we now think about the way in which we manipulate quantum coherence in matter for applications, like how we make a quantum bit and how we manipulate those quantum bits. Really grew out of this line of research. And there are some real towering figures in that, like Rabi and Ramsey. I mean, if anyone who saw Oppenheimer, saw Ramsey trying to make sure that Oppenheimer ate something. He was really, everybody in this field, he's like the Genghis Khan of this. Everybody's related academically somehow to Rabi, so am I. So we'll talk about this as well. This will really be a lot of the starting point. Here, to start, we'll think about the way in which electromagnetic fields, even when thought about classically, classical fields can create quantum coherence in matter. We'll then talk about the quantum nature of the field itself, and then we'll think about how the quantum field relates to the quantum matter, and there are new ways in which those manipulations can happen. Now, intertwined with all of this, and this is where, I was trained as a quantum optician. I need little glasses, no. And the reason I got into quantum optics was because I was interested in the foundations of quantum mechanics. And really that was the forum in which, I like to think we were the Muslims of the dark ages of shut up and calculate. We kept the faith alive while everyone else was ignoring the foundations of quantum mechanics, and the quantum opticians were the people who said, no, I really, want to understand what those inequalities were and what decoherence was. And a lot of the foundational experiments on the foundations of quantum mechanics were and have been done in the context of quantum optics, in terms of both of these pillars of quantum optics. And so we'll make all of those connections as well. It's really an interesting way in which we gain a deeper understanding of quantum mechanics through our ability to treat very simple systems, and for the experimentalists to manipulate very simple systems like individual ions or atoms or photons, okay? So this is the map that we will be going back and forth between, and there's different aspects and different textbooks, and there's no one that covers them all, so you're stuck with me. All right, very good. So, let's continue then. So, as we were saying, quantum optics has been very important from the beginning and continues to be important in the context of the foundations of quantum mechanics. And let's just review just a few little things about the history, because it's important. Though these historical things that, you know, seemed really boring when we first maybe learned our modern physics, actually we'll be reminded about them, and they will become important again. You know, of course, in 1900, Planck's theory of black body radiation was the birth of quantum mechanics, right? The introduction of the quantum of action was born in Planck's study of the thermodynamics of light and the ability to try to understand what was being seen in the Wien law versus the Rayleigh-Jean law, and putting it all together required Planck to come up with this empirical law, and somehow explaining what we saw, you know, with light at low energies already required us to have a quantum theory. The classical theory was insufficient. 1905, Einstein's paper where he introduced the photon. I say the photon in quotes because he actually never used the word photon. The word photon was invented in the 1920s by actually a chemist, and it was picked up by Compton when he did the experiment, when they really decided. There's a lot of controversy, we'll come back to this, about whether, you know, Planck's theory, we learn about it now and thinking about it as quantizing the field, but that was not how it was understood for, you know, 20 years plus. And that's going to be a subtle point we'll come back to. Under what conditions do we really need to describe the field in terms of photons? And in what context does a classical theory suffice? I mean, what this paper was really about, was about this. So what Einstein, it's fun to read this paper, by the way. I might send it to you. It's very interesting. You know, this paper is most famous for the photoelectric effect. But most of the paper isn't really about that. What this paper is mostly about is saying, can we understand the Planck theory by thinking about the field as being composed of quanta of light. Now, of course, you know, at that time, you know, from the late 19th century to the early 20th century, where physicists were really focused and where the cutting edge was the idea that, in fact, matter was corpuscular in nature, right? There were atoms and molecules, and then electrons, and there were particles, right? And that was discovered not that long ago. And the statistical physics helped people to understand thermodynamics and the statistical fluctuations arising from the fact that there wasn't a smooth continuum of matter led to great understanding of the nature of gases and you know, matter more generally. So Einstein tried to see whether he could understand the black body radiation by saying maybe light is corpuscular in nature. Maybe there are individual fundamental units of light, which were called quanta of light, and you know, and from that just use thermodynamics to try to derive the Planck law, and it worked. Okay, so that was, of course, you know, part of the whole story, you know, deploying all over about wave-particle duality. You know, when we think about quantum optics, what we're going to learn over this course of semester is some of the features we see and we measure are really just coming from the fact that light itself is corpuscular. Some of the fluctuations we see in measurements, some of the quantum noise, as we call it, that we see in measurements is coming from the fact that light itself is made up of these indivisible units, which we now call photons. That's, you know, different than the whole story about quantum coherence. And so let's get into that a little bit. You know, of course, this is, yeah, when was it? Let me get my notes here. 1893 was the Young double slit experiment. 1803, excuse me. I know there was an 1803, but yeah, it was a lot longer ago than that. You know, this definitively, you know, put to rest Newton's particle theory of light. Light was a wave, and the definitive property of waves is interference. So we have a situation we might sort of have some wave coming in through a pinhole, and then it comes through these two slits. And what we see on the screen, of course, is a pattern of intensity that has interference fringes of bright and dark places. And as we know, this arises because there is interference that is associated with the electromagnetic wave. The waves we now, of course, know are waves of the electromagnetic field, and there are two different paths that the wave can take, for example, if these are very small pinholes, and then there is interference such that the intensity at this point depends on the interference of those fields, okay? But now all of a sudden we have this story of the corpuscular nature of light. Interestingly, so you may or may not have learned in your modern physics courses, I mean, it's often part of the history that at least I learned, and I think many of us learned, that in 1909, J.J. Thomson and G.I. Taylor did an experiment that showed that photons interfere. Did you learn about this experiment? It was an experiment. J.J. Thomson famously discovered the electron, and Taylor was an undergraduate student, and Taylor was given this assignment by Thomson to say, what if we had feeble light? So what was done was there was some kind of Bunsen burner or something like that, and then there was an attenuator which made the light very low in intensity. It was feeble. And then they had like a needle or something that diffracted the light. And there's a photographic plate. And what was seen was, the photographic plate collected dots and recreated this interference pattern. And this is often stated in modern physics books as the proof of the existence of the photon interference. That this was the first experiment that demonstrated that. But it's actually a very subtle point. And although the light is heavily attenuated, and you might say, from the point of view of thinking about photons, there are few photons coming through, hitting this barrier, this needle, and then diffracting. This source of light is a classical source. Now, what we call classical and what we call quantum, you might say, that's just semantics. But as we will understand in some few weeks, we can completely describe this experiment without ever quantizing the electromagnetic field. We don't have to have a quantum theory of the field. What we need is a quantum theory of the matter and the way in which the matter interacts with the field is quantum. And that will completely explain this. And in fact, it was fun. I just went back to try to find this paper. I mean, actually, Taylor was, he wasn't trying to prove anything about photons, just Thomson said, hey, let's see what happens with very feeble light, and it showed this property. But it was later in, after the Comte turn said, we go back to that experiment by Taylor was actually the first to demonstrate the existence of the photon. And that first experiment wasn't really done until 1986, and we'll talk about the real experiment a bit later. Right, so, quantum coherence, I said, is the unifying feature that will connect various threads in what we're discussing in this course. And I haven't really even defined what I mean. So let me just begin with my definition of coherence. Coherence is the ability of a system to exhibit interference. That's how I'm defining it. So, in the Young's double slit experiment, in this case, a single pinhole was placed before the double slit because the incoming sources that they had did not have significant coherence at distances between the two slits. By putting this pinhole here, you created something that had good spatial coherence. That's to say, you can see interference at different points in space. So the pinhole in that experiment was necessary to create the coherence in order to observe the interference. You need coherence to get interference, okay? Let's just remind ourselves and say some things about classical interference. So to do that, I'm going to think about, instead of thinking about the double slit experiment, because there's all these different ways I can get to different points on the slit, I'm going to think about a simpler problem of temporal coherence. So here's my little diagram. This is our favorite toy interferer, the Mach-Zehnder interferometer. For light, okay? So what is this diagram mean? Okay, so I have a beam of light that says enters into this interferometer. And what the interferometer does is it measures the interference between different paths that the wave can take, okay? So what we have in this case is a beam splitter, which is partially transmitting and partially reflecting of the wave. We have a mirror on each port, which then recombines the beams on another beam splitter. And then I will imagine I have, let's call this B and A, just to be consistent with my notation. We have two, what I'm going to call square law detectors. At each of the output ports, okay? And what does the square law detector do? What the square law detector is, it measures the intensity of the beam, okay? And so the question is, I put in some amount of power or intensity into the interferometer. Some of the energy gets divided, it gets recombined over here, and then I want to know how much intensity comes out here and how much intensity comes out here. Okay? As a function of what? As a function, I might be able to, move one of these mirrors by some amount, delta L, the difference, and so I might have some path length LA and some LB, and as I look at the path length difference, I want to know how much of the intensity comes out here and how much of the intensity comes out there, okay? And that depends on the interference of the waves that are incident on this final beam splitter. Right? So let me just quickly say a few words about classical electromagnetic theory, just very basic stuff, just to remind us so we're all on the same page with the same notation. Okay? What we mean by the intensity is the time average of the magnitude of the Poynting vector, okay? So S is E cross B, and because you have to live with me for at least one semester, if not two, you're gonna have to learn Sanskrit, also known as CGS units, because they're God's units, and I only speak in God's units. You know, today I can be God, whatever. So this is the Poynting vector. And the intensity is the time average of that. So that is to say, I'm looking at the time average of this where T is the period of oscillation of some chosen frequency. All right, so let me make a little aside over here. And just say a few words about some of the notation we're going to use when thinking about monochromatic fields. Monochromatic means that there's a single frequency omega, okay? And if I'm thinking about a monochromatic field, that means is I have some function of time that's oscillating with that single frequency. It has some amplitude, and there's generally some phase, I'll call phi, which is to say that if I look at this function as a function of t in units of omega, then it looks like this. Where this is the phase at which this thing has the maximum amplitude, okay? And this is the amplitude. Now, if I have a field that is monochromatic in this way, then, of course, there's a few different things I say. I can write it like this, of course. I'll call this amplitude x and this amplitude p for reasons that will become clearer a little bit later, okay? These two parts, the part that oscillates like cosine and the part that oscillates like sine relative to some chosen zero of the phase, are known as quadratures of the field. They're called quadratures because they oscillate 90 degrees out of phase with one another, so they're in quadrature, okay? And so one of the things we notice, and it's, as you know, is convenient when thinking about functions that oscillate a single frequency, is to think about these real functions as the real part of a complex function. So it's convenient then to write this function as the real part of x plus ip e to the minus I omega t, which is equivalent to a e to, oops. So this function, which oscillates at this frequency, can always be written as the real part of a complex amplitude. Where the complex amplitude has a real part and an imaginary part, and equivalently, it has an amplitude and a phase. Okay, and they're obviously related in terms of the magnitude. You know, this is the square root of x squared plus p squared, and this is the arctangent of p over x. Okay, and so all the information about, if I know I have a function that is oscillating with a fixed frequency, I can always express those two parameters, the amplitude and phase, or the two quadratures, in terms of a complex number, as we know, and that's very convenient. And so, what's also a thing to remember is that if I have another function g, which is also monochromatic with the same frequency, it has its own complex amplitude, and I look at the time average of the product of those two functions, then I can always just do that very quickly. I mean, this is like, this is 1/2 this plus its complex conjugate, and similarly for f. And so when I plug that in and do this time average, it's easy to see that what I get is 1/4 f g star plus f star g, which is equal to 1/2 the real part of f g star. A very convenient way of calculating time averages for functions that oscillate with a single frequency in terms of their complex amplitudes. Okay? So for example, that means that the time average, I'll use the bar for the time average of this, is equal to 1/2 the square of the complex amplitude, f star. Right? Very good. So with that said, we can come back over here to calculate the intensity. Before I do that, I should maybe say, for our field, if I have a monochromatic electromagnetic field, then say the electric field as a function of position and time will be equal to the real part of some complex amplitude as a function of position, e to the minus I omega t, right? And if I have, this is a, for a plane wave, then we know that the electric field as a function of position, which is, say, polarized, so I have a polarized plane wave, then there is some polarization vector, and then I have some amplitude, E0. It might have some phase, this is that, and then, oh, I don't want to, there's too many tildes. There's gonna be another. And then this is this. Okay? This thing often we will call E tilde. It's the complex amplitude which has the magnitude and phase relative to everything else. Okay? So with that said, then I have the similar thing for the magnetic field, which of course has this in the direction orthogonal to K, and it's the other direction. And so the intensity in this case is equal to 1/2 times that, or C over 8 pi, the real part of E0 tilde, B0 tilde star. Right? Now, of course, in a plane wave, in God's units, the electric field has the same magnitude as the magnetic field. It should, well, of course it has to have the same magnitude, because they're just in a different reference frame and E goes to B, so why would they have different units? That's ridiculous. They should have the same units. And so that's the magnitude of E squared. Okay. Now, often we'll just forget about this. This is just some constant. And when I say the intensity, we'll just say the intensity is equal to E squared. Of course, it's got a C over 8 pi in it, but we just don't need to carry that around. So often we'll just think about the square of the amplitude when we're thinking about what comes. I mean, if we needed the actual number in some, watts per square centimeter, then, we would do that. Okay. All right. So with that said, let's calculate what is the intensity output at these two output ports of this detector. Okay, so for that purpose, we need to think about how the field is transformed as it goes through this interferometer. Okay, so the first thing we need to do is think about a beam splitter. So a beam splitter is something which partially transmits and partially reflects waves that are incident. And this is a 2-port beam splitter. There's a port here, we'll call port A, and a port here, we'll call port B. So we have an input electric field complex amplitude here, and an input complex amplitude in B. Okay? And then we have an output electric field in this port, and an output electric field in port B. Okay? So the question, this is a scattering transformation. If we wanted to really solve this problem, from first principles, we'd write down Maxwell's equations and we think about scattering. But, we know what happens. What we know is that there is an amplitude that tells me how much is transmitted, and an amplitude that tells me how much is reflected. So I can think about these 2 ports as a transformation on 2 modes. The term mode is going to be very important in our discussion, and we'll define it a little bit more precisely soon, but let me just be fast and loose with my language at the moment, and just say these 2 represent 2 modes of the electromagnetic field, and they're transformed by this beam splitter. So what that tells me is that the output amplitudes, complex amplitudes associated with the field are related to the input amplitudes by some matrix, a 2x2 matrix, okay? And the reason it's a matrix is that this is linear optics. So this is not nonlinear optics. Maybe, I don't know what number that 569, I don't remember anymore. But we're assuming that there's a linear optical transformation. So that means that there's a linear input-output relationship between the fields, okay? And so that linear relation is described by a matrix. What is that matrix? Well, there's the output here is the transmitted portion of this and the reflected portion of that. Now, I'm going to assume this particular beam splitter is a symmetric beam splitter. We don't have to. Many of the ones in the lab are not symmetric, but I'm going to assume if I flip it over, it's not coded on one side differently than the other, okay? We could have a T12 and a T1R, you know, but I'm not going to do that here. And so similarly, B, so you see that this is a symmetric beam splitter, where T and R are the transmitted amplitude. This is these are complex numbers. So T has some magnitude. I'll say the magnitude squared of T, I'll call is typically called capital T, and the magnitude squared is called capital R, so that T is the square root of capital T with some phase shift. So the beam splitter both changes the amplitude and the phase, generally, of the waves that are incident upon it, okay? Now, let's imagine that this is not only symmetric, it's lossless. If it's lossless, what does that tell me? It tells me the total energy that comes in must equal the total energy that goes out, which means that it must be the case that the intensity in summed over both input ports has to equal the intensity out summed over both output ports. But what that tells me is thought of as a vector in a complex vector space, that the norm of this vector has to equal the norm of that vector. So what does that tell me then about this matrix? Yes?
T plus R, big T plus big R is 1.
That's one thing it tells me. For sure, big T plus big R has to be 1. Ivan Apollo is right. But what would you tell me about the matrix? It's unitary, okay? So this matrix is unitary. It's the scattering matrix, sometimes known as the S matrix. Don't get it confused with the Poynting vector or the spin or something else we'll call S at some point. Okay. Yeah, exactly. So that's the S matrix, which is unitary. It's a scattering matrix. It's a unitary matrix. And so let's just say a little bit more about that. A unitary matrix is one that, when I look at it times its adjoint, which is its conjugate transpose, in this case, that's just the conjugate because it's a symmetric matrix, that this is equal to T squared plus R squared, and then the off diagonal is T R star plus R star T that has to be the identity, since that is the definition of a unitary matrix. So, as was said, one thing is these two coefficients have to be 1. That's this. We have another fact, though, which is lesser known, which is that this has to be 0. And, sorry. That has to be 0. Okay? Which is to say that the square root of t times the square root of r times e to the I phi t minus phi r plus the complex conjugate has to equal 0. Or said another way, the cosine of this phase difference has to be equal to 0, which says something about the relative phase, that the relative phase must be an odd multiple of pi over 2 for a symmetric beam splitter. Okay? So for a symmetric beam splitter, the phase difference must be pi over 2. Now, often, because at the end of the day, we're looking at square law detectors, which detect the intensity and not the field itself, we're not interested in the overall phase of the field that comes out to my detector. I'm interested only in the intensity, which means that I don't have to worry about the overall phase. I can think about just the relative phase. That is the only thing that matters in the transformation. So for example, in a 50-50 beam splitter, not a 50-50 beam, in a symmetric beam splitter, I can just choose the phase of, say, t to be 1, so that's to say, make this phase 0, in which case this guy can be, for example, pi over 2. Okay? So that kind of transformation says something about the determinant of this matrix. So if I look at the determinant of this matrix, that's t squared minus r squared, which is e to the 2 times that, minus e to the 2I pi r, which is equal to e to the 2I phi sub t times 1 minus e to the 2I phi r minus phi t. Right? And for a symmetric beam splitter, this is a multiple of pi over 2. And so this is a multiple, this is pi, which means that this is minus 1. Oh no, I know where I went wrong. I forgot the TR. Excuse me. So there's a T minus R. Okay. So this is e to the 2I phi sub t plus R, which is 1. So generally, the determinant of this thing will depend on that phase, but if I choose it to be 0, which I can, without affecting anything about that, then what I get is this determinant is 1. And often, typically, the set of unitaries we choose to deal with in these kind of problems are ones where we don't care about the overall phase, in which case they're not general two-dimensional unitary matrices, but they're special two-dimensional unitary matrices, hence the name, the group SU2. So often when we think about these transformations on these two modes, since we don't care about the overall phase if we're measuring the intensity, we can take that overall phase out, and taking that overall phase out is equivalent to looking at the set of matrices whose determinant is 1, and those matrices are the matrices that are known as special unitary matrices, or SU2. We're going to be talking about SU2 a lot. So this is our first introduction to SU2 here. Right, so with that said, let's continue and think about our transformation on these matrices a bit more. I mean, transformation on the fields. So we have a 50-50 beam splitter. That's a case where half of the intensity is reflected and half of the intensity is transmitted. The S matrix, for that, we can have plus or minus I, it doesn't matter, but for simplicity, I won't store another negative sign in there, okay? So that's the symmetric 50-50 beam splitter. That's the S matrix. Let's come back over here and think about, okay, what is the field that's incident as I propagate from one point in space to another? So if I start here at some input point, this is the electric field, say, at some initial position at some incident time, and I ask if it's freely propagating, what is the field at this position at whatever time I measure it? How are these related if I propagate a distant cell in free space? Right. Well, in general, it's related by the retarded time, right? So the field here is what it was at the initial point at the time t minus right? Because what I'm seeing here is what happened over here in the past, okay? And so if I have a plane wave, in that case, what that says is that the output complex amplitude is going to be equal to the input amplitude. I mean, e to the minus I omega t goes to e to the minus I omega t, t minus L over C. But that's equal to the input omega c over L, or e to the I k L. Okay? So when I propagate, I pick up a phase shift depending on the distance that I propagate. Okay, so there's going to be, on that case, I'm going to pick up, there's a propagation, I'll call that matrix M, which says on one port, I pick up that, and on another port, I pick up that, which represents those two paths. Is this an SU2 matrix? Is it unitary, first of all? Yes. So multiply it by its conjugate transpose, I get 1. Is it special? Well, everybody's special, but is this one?
Depends on K.
No, it isn't, generally not. We can factor out, if we wanted to, an overall phase. I'm sorry my handwriting is less than wonderful. Another word for terrible, but I'll do my best. Everyone see that? So this is, I can neglect this if I wanted to, because it doesn't matter, the overall phase, and now this is an SU2, because its determinant is 1, okay? So, let's put it all together here. There's one last thing that happens, which is the mirror is doing the old switcheroo and is taking what was port A into the input port B, and what was in port B and putting it into the output port A.
The solid mirrors are also making changes.
Say?
The solid mirrors, the non-transparent, they're also
Right.
making
Yeah.
signs.
That's correct. I mean, really, we should put in a minus sign for the reflection, but again, that's an overall minus sign, and I don't care. Maybe we should. Okay, so putting that all together, what we have is that the output amplitudes out of those two ports is the following. First, I have the S matrix, the scattering, which is the 50-50 beam splitter acting on this. Then I have the propagation. I have the switcheroo, which puts port A into port B, and then I have the scattering matrix again. And when I put that all together, I get the following thing. This is an exercise for the reader. So the total effect of the Mach-Zehnder interferometer, which we will often just abbreviate as the MZ interferometer, is this SU2 matrix acting on this vector. It's SU2, it's got to be unitary because it's lossless. And so we had to preserve the norm, and because we didn't care about the overall phase, we got rid of all of that stuff. Okay?
I didn't get that.
Sorry, Siri. Not Liz talking to you. Sorry. I have to turn that stuff off. All right, so let's just conclude, though, with the following. What does this tell me, then? So let's say that this, for example, was 0, as it was here. We were putting nothing into this input port. Okay. So what that tells me in this case is that the intensity in output port A is the square of this amplitude and the intensity in port B is that. Or, if we remember trigonometry, that. Okay? Which says what? Okay. Let's imagine that I had a balanced interferometer where these two paths were exactly equal in length. So delta L was 0. How much intensity would come out here? 0. All of it comes out here. If this difference is such that the phase difference between these is pi over 2, then all of it comes out here, and none of it comes out here. And so I see these kind of interference fringes, if you like, as a function of the distance, the delta L in units of K, which looks like this, with the anti-nodes and nodes in opposite place, where this is, and that's the intensity in the output port A, and this is the intensity in the output port B. Now, this is a fairly elementary, I went through it pretty quickly, but man, this is one of the most important things. I mean, this is two-state interference. We are going to return to this over and over again in different views of it, right? For those of you who are familiar with qubits, I mean, this is the rotation of a qubit, but it is at its base just thinking about interference of waves and phase shifts. So it's important for us to put these different concepts together. The concepts of interference are so crucial to all of this. It's just so important to just do this most basic problem